Hello, everyone. I'm Whitney Espick, and I'm CEO of the MIT Alumni Association. Welcome to the October MIT Alumni Forum. Over the past few years, the world has watched the astonishing rise of generative AI. Tools that draft essays, compose music, and mimic human conversation have moved rapidly from research labs into everyday life. And just recently, new systems have made headlines for passing graduate level exams, generating entire films, and coaching job seekers through interviews. Yet all this buzz raises a deeper question. Are we simply applauding machines for copying human work, or are we challenging them and ourselves to imagine something greater? To help us think beyond the limits of automation and replication, we are delighted to welcome Sendhil Mullainathan, the Peter D. Flores Professor of Economics and Professor of Electrical Engineering and Computer Science at MIT. Professor Mullainathan is a behavioral economist and a leading thinker on the human side of algorithms. A recipient of the MacArthur Foundation's Genius Award, his work bridges economics, computer science, and human behavior. At MIT, he leads the Bike Shop, an initiative to create more human-centered AI, which he believes is akin to bicycles for the mind. Guiding the conversation today is our moderator, Anne-Marie Michael, Assistant Dean for Development in the MIT School of Humanities, Arts, and Social Sciences. Anne-Marie brings extensive experience connecting research and ideas with the people who put them into practice. If you already have questions for today's discussion, please add them to the chat box below. You can upvote the ones you find most interesting. And also, closed captioning is available, which you can access by selecting the CC icon in the lower right corner of the video player. And now, over to our featured speaker, Professor Mullainathan. Thanks so much.
Thank you, Whitney, and thanks to the Alumni Association for having me. I'm just going to dive right in. Let me get my screen shared here. All right, fantastic. So I want to start with a conference I went to a couple of weeks ago. It's called the Economics of Transformative AI. And what is transformative AI? It's AI that can do everything that the smartest people could do. This is a very provocative question. What would a world look like in there? But it can't help but wonder, that's just a remarkably ambitious goal. But you also can't help but think it's a kind of unambitious goal, as Whitney put it forward. And I want to argue today that there's a much more ambitious goal that we ought to be aiming for. And to do that, I want to tell you that this second goal, not the road we're on, but the road we could be on, is one that could make all of us better off. So what's this other road? Well, let's start with The Wizard of Oz. I'm sure many of you have seen this movie. I don't know how many of you have read the book, but, in the modern era, you don't need to read a book. I just went to ChatGPT and said, what is The Wizard of Oz? Please keep it short, simple. I can't be bothered to read things. So I got a good summary. This is ChatGPT's summary of The Wizard of Oz. Now, I could have actually just gone online and searched for a good summary, and I think I would have gotten a much better summary. Transported to a surreal landscape, a young girl kills the first person she meets and then teams up with 3 strangers to kill again. So it's unfortunate ChatGPT didn't give me the best summary, but this was a workable summary. In many ways, this is probably a canonical use of modern AI. It kind of made my life a bit easier. What would be a different use of AI? Well, let's actually go back to this first book, The Wizard of Oz. If you haven't read it, you probably haven't read the second book, or the third, or the fourth, or the fifth. There are actually 30 books of The Wizard of Oz. And of these 30 books, 2 of them, or rather one of them, is particularly interesting. It's called The Royal Book of Oz. It is the 15th book. And as you've already heard, I'm not such a big reader of Oz books, but I find this book very interesting. Not because of what's inside of it, but because of the cover. Here are 2 covers of this book. And if you stare at them long enough, you'll realize there's something odd about these 2 covers. And they have the same illustration, but they don't have the same author. You see, one says that this book was written by Frank Baum, who wrote the original Wizard of Oz and wrote book 1 through 14. The other says this book was written by Ruth Plumley Thompson, who actually wrote book 16 through 30 because Frank Baum died. But nobody knows who wrote the 15th book. That is, until this paper showed up. Does only the Oz himself know who wrote the Royal Book of Oz? And this is a book that analyzed, using an algorithm, who wrote the 15th book of Oz. Now, this is a very different use of algorithms. And I want to explain to you what this book did. I'm going to give you sort of my own little rendition of this paper with not more than it took quite a bit of literary license, though I won't change any of the conclusions. I just made it, a little bit more palatable. So here's what, in a nutshell, this algorithm did. It was taught to identify Baum texts and Thompson texts. Remember, these are the two people who wrote the beginning of the book, at the end of the books. And the way you did that was you took the books that we knew, who the authors were, 1 through 14, 16 through 30, broke them into little nuggets and said, look, these pieces were by Baum, these pieces were by Thompson, and you trained a machine learning algorithm to sort of start detecting the patterns. And on new text it's never seen, it can say whether it's Baum or Thompson. The astonishing thing about this paper is what this algorithm, how well it does. Here's books through 1 through 14, 16 through 30. Remember, these are text pieces from those books that it had never seen. For 1 through 14, it gets 100% right. It says for sure it is Baum, and it is correct. They're all Baum. For books 16 through 30, it says for sure it's Thompson, and they're all Thompson. Now, you might have thought, I could really not care about this, but I bet at this point you're wondering, what does it say on book 15? The book that nobody, all these literary scholars who are trying to figure it out, have not really been able to figure it out. Well, let's zoom in a little bit. Let's go chapter by chapter. If you go chapter by chapter on book 15 and ask, how sure is it? Which chapter was written by people? It says, oh, I know what's going on. Until 12, it's Baum. And after 13, it's for sure Thompson. In other words, the algorithm here could see perfectly what literary scholars who carefully read the books and tried to make sense of things that they weren't able to come to agreement on. But it's like night and day for the algorithm. And it's amazing to think about it. Here's the kind of text it was given. This is the beginning of the book. It's like, this isn't 5,000 words, but it was given these pieces of text. It was just given this. What is it seeing here? Well, for you to appreciate what it's seeing here, I have to just tell you some facts about English and language. There are actually two kinds of words in all languages. Content words. These are the words that you know. They carry meaning, they're stressed, you notice them, they're nouns, they're verbs, they're adjectives, they're adverbs. What other kinds of words are there? Well, there are these function words. They just kind of connect things like the, a, am, this, that. They're just the glue between the nouns and the adjectives. As people, we notice content words. We don't really notice function words. But content words are not the most common words. The most common words are these function words that we never notice. I, the, and, to. But as I said, they're invisible to us. One way you can see they're invisible is take a look at these signs. It takes some time to notice what's wrong with these signs. There's a problem. But it'll take you a while to see, or at least most people, it'll take some time to see that the function words, the are repeated. A is repeated. But because they're invisible to us, we don't notice this. And in fact, the second miraculous thing about this algorithm is not just that it knew that it was Baum and Thompson, but which things it used. It did not actually use the entire text. It only focused on the function words. This is all it saw. Everything else was masked. Just from these function words, it manages to figure out who the writer is. Now, I'm telling you this because you'll notice how different this is. In one case, we talked about an algorithm that can do everything the smartest people could do. But in this second case, we're talking about algorithms that can do what even the smartest people cannot. And these are the two kinds of AI I want to describe. Now, of course, the Wizard of Oz is an important topic, as I'm sure we can all agree. But for this second category of algorithm, you actually know another algorithm or have heard of one that does this. It's not ChatGPT. It's not a large language model. It's AlphaFold. When AlphaFold won the Nobel Prize, it was a remarkable, or the creators of AlphaFold, it was a remarkable achievement. What it did was it answered the question, I have a protein, which is just a sequence of amino acids. What will be the folded structure of that protein? We kind of know the organic chemistry of how they fold, but we don't know how it all aggregates together to form a shape. AlphaFold was a significant advancement in being able to predict how it folded. It was an important problem, but it was a very hard problem. One that people weren't able to do, but now we had an algorithm that could do it. So this idea that was in the Wizard of Oz is not some idea that it's obscure. It's a kind of algorithm. Now you'll notice something. This is a kind of algorithm that was built by DeepMind, by Google. The very same companies that are now building these language models also have built this kind of algorithm. And what I want to talk through before I go through some examples is these two kinds of AI have very different properties. And I hope to convince you that we should very much be on the path that looks like AlphaFold and not on the path that looks like large language models. And I'm going to do that by just contrasting what these algorithms can do. I've already talked about one difference. Of course, it's does what people do, does what people cannot. But there's another key difference, and this is super important. ChatGPT is also constrained that it cannot do what people cannot. But AlphaFold cannot do a bunch of things people can. No one thinks, I want to learn biology. Let me go talk to AlphaFold. I want to have something explained to me. AlphaFold does not aspire to do the things humans can. It aspires to do things humans cannot. It's a specialized model that does that amazingly well, but it doesn't try to do this other base. That's going to prove very important because so much of what we spend our energy and time doing right now is trying to get that last 4%, 3% on benchmark performance. But trying to get something so close to human is actually quite costly, and it's not obvious we're being successful at it. AlphaFold just takes a different path. Hey, here's a much harder problem. I'll do that and not worry about the stuff that people can do. As a result, on the path on the left, when we build these models, if we are very successful, we will have created substitutes for humans. On the right, because the AlphaFold path has something that can do that people cannot, but people have something to do that it cannot, we have something that actually complements people. As a consequence, if you ask most people about AI, the main question that they have is, what will this do for jobs? Well, there isn't an it. It depends on which kind of AI we're building. The AI on the left, it's natural why people think that's going to lead to job loss because it's substituting for people. But the AI on the right, you notice it's actually creating jobs. Take biologists. The field of biology just got more productive because of AlphaFold. The returns to hiring biologists have just gone up because the biologist, the person, can now do more because one of the things that they weren't able to do is now we can do with AlphaFold. So that leaves all the other activities are now more complementary. They're not blocked by this incapacity. So not only do these things have different capabilities, they're built very differently. And that difference in building has some pretty stark ramifications for a bunch of the negatives that we associate. So if you think back and say, what do people dislike about AI? And think that there are problems besides job loss. I think a lot of the things they dislike come from the way they're built. So let's just start with how is like a large language model built? Well, I think by now most people have heard this is trained on the entire corpus of data that's digital, all books that are digital, and the internet. So another way of saying it is that this algorithm is trained on the knowledge we have. How is AlphaFold trained? It's actually trained on ignorance. Here is a data set. Here's the protein. Here is how its folded structure looks like. I don't know how A goes to B. I have no idea. That's my ignorance. I present many instances of my ignorance to this algorithm and hope it can figure it out. There's something quite beautiful about training an algorithm on ignorance. It's not just beautiful, it also gets rid of all the copyright concerns we have. You have this sinking feeling that is a language model producing anything? It probably is. We don't know. We can have conversations about it. But the reason we have those conversations is because we feel it's in some sense expropriating all of the creative human activity that went into its corpus. After all, when it writes a very nice headline or makes a very nice image, all of those things are in some sense variants or copies of something in its training data set. And we wonder, I mean, shouldn't the creator of that get some attribution? None of that happens with AlphaFold because the only thing we're giving it is ignorance. It isn't expropriating our knowledge, it's illuminating our ignorance. The other thing to note and this goes back to the point I made earlier, is that large language models, it takes a lot to copy human beings. They're huge models. They're unbelievably enormous. In contrast, because we have this focus model challenge working on a very focused problem, these are actually small, quite small. Recently, a very nice open source version of this came out that you could run on your desktop, and it runs very well. These are not large models. They're specialized and can do a lot. And as a result, while the stuff on the left is a massive energy sink, huge amounts of energy are going into just having this explain the Wizard of Oz to me, which might not be the best use of energy in the world. On the right, because they're such small models, it's much less costly than me playing a video game tonight. So with these two kinds of AI, I hope that I've helped you see that the differences, the social implications are fundamentally different. Job loss versus job gain, expropriating creators versus not expropriating creators, actually adding to the stock of creation, an energy sink versus something that's actually quite easy to make inferences. There's one other very big difference between these two, which I want to flag. If I look back, as people have done over the last 2,000 years, and people have produced graphs like this and looked at GDP per capita to the best that we can estimate it around the world, we've had an astonishing amount of progress. It has been an exponential growth for the last two. It is insane how much wealthier we are today. And every decade and century on century of progress is just exponential growth. Economists who have looked at this have come to a conclusion that I think is obvious, but I want to flag. The pace of human progress ultimately, in the long run, is dictated by the pace of innovation. We grow because our ignorance goes down. We grow because we innovate. We grow because we understand new things. And that says that if you care not just about jobs, but about growth, the AI on the left that does what we do can't really contribute to growth. It's going to save some dollars, maybe a lot of dollars. That's why companies are after all of this, because, hey, if we can cut a bunch of jobs, that's a lot of money at the stake. Yes, it can produce some dollars for some companies. But to the extent it's just giving us in a box what we can already do, that's not going to change fundamentally the pace of innovation. Around the margins, it may do some things, but that's about it. On the other hand, AI of the AlphaFold kind is a fundamental new fuel for economic growth. It gives us the possibility of changing the very nature of how we innovate. Let me try and bring these ideas alive and help you see how it applies. Obviously, it applies in science. You've seen AlphaFold. Let me explain it in three different areas. Healthcare, something that seems like this shouldn't work in, criminal justice, and education, just so you get a sense of what it means to discover. So let me start with healthcare. In healthcare, I want to tell you about a problem called sudden cardiac arrest. Sudden cardiac death, I should say death, is a situation where it's disproportionately men kind of frighteningly, roughly my age, suddenly fall over dead. It was sort of a sudden heart condition. The thing about sudden cardiac death is that we can do with it what we did with the Royal Book of Oz. Remember, there we gave it expert judgment to automate, or we gave it ground truth to do discovery. Well, here, let's give a set of EKGs, and let's have doctors look at these EKGs and tell us, does this person look like they're at risk of sudden cardiac death? We could train an algorithm to copy that. That would be like the automation approach. Now, it turns out if you do that, you don't get very far. The reason you don't get very far is take the algorithm out of the picture. Have a doctor look at all of these. Most sudden cardiac deaths are a medical mystery. We don't know what, maybe there's nothing in the EKG, but certainly something was wrong in the heart. Maybe the EKG doesn't pick it up. Would an algorithm fare better? So what we did is we went and got a lot of such EKGs, and a lot of people who did die in this way in Sweden got their last EKG and got other people who didn't die, who had similar looking EKGs. and asked, could an algorithm notice differences that doctors couldn't? And it turns out that it could. So here I'm just going to show you, I won't walk you in tedious detail. These things are not fun to look at on Zoom, but I'll just give you the gist of it. Here, we built this algorithm. We then asked, how good is it at finding high-risk people? The thing you should know is there's a risk threshold. If we find people above this threshold, it's a huge win because all we need to do is to put in a pacemaker. These are people we could just put in a pacemaker. When their heart gives out, the pacemaker restarts it. It's all fine. And at that threshold, it finds a huge set of people that would have that did die historically, but the algorithm would have said, put a pacemaker in this person. These are people, when you give these EKGs to doctors, they don't really notice anything at all. And as a result, not only are we finding people that we could have intervened on, we can start looking at those EKGs. So you can see here, I've shown the low risk and the high risk EKGs, and start noticing patterns that doctors had not noticed. And now we can start getting into the mechanisms of it. Like, what creates these patterns? What in the heart is it? What about sudden cardiac death did we not fully understand? So that's the first application of what it might look like to build an AlphaFold AI rather than automation AI. Let me give a different example, a much more grim example, given the context of criminal justice. Every year in the United States, there are about 12 million arrests. And right after people are arrested, there's a question that has to be answered. Where do they wait for trial? Well, there are two ways we could approach this problem. We can approach this problem by training an algorithm that does what the judge does. That would be the automation approach. You can see all sorts of problems with that. We are simply then automating whatever limitations, biases, whatever you will, that the judge has. And in fact, you worry that if the automation is slightly less than perfect, you might actually be losing some of the judge's humanity and keeping only their biases. But what if instead of training the algorithm on what the judge would do, which is what means to train on the corpus, we actually trained on an algorithm on the thing we didn't know anything about. The thing we didn't know anything about is the judge is trying to predict risk. What if we tried to predict which person, were they to be released, would actually go on to commit a serious crime, a very violent crime? Well, now we have the chance to build an algorithm that discovers stuff. When you do that, you actually find that such an algorithm can improve decisions quite a bit. It's able to keep jail populations fixed and reduce crime by 24%, if that's what you wanted. Or because you're finding the risky people, you can say, you know what, I'll cut jail populations. You can cut jail population by 40% and still have the crime rates we have today. 40%. This is like closing Rikers in July. Moreover, because the algorithm is looking at the real underlying risk and not what a human would do, it actually reduces racial disparities. Now, notice, I'm not saying we should automate it all. I'm just saying an expert here could use some help because the algorithm has discovered signals it hasn't, that it didn't have. In fact, we can go further and ask, wait, what are judges getting wrong? We can turn the camera on the judge and ask the algorithm to tell us, hey, can you help us discover what kind of mistakes the judge might be making that we didn't think of? When we do that, we start to learn what factors predict the judge's decision. It turns out the fifth most important factor that judges seem to overweight is whether the current charge is a drug crime. The fourth most important factor is whether the current charge is a felony crime. The third is So you can start to see a pattern developing. The legal scholar Cass Sunstein, based on these results, has sort of coined the term current charge bias. It appears judges overweight the current charge. But the number one factor here is a little different. It's the current charge of having the wrong face. The single most predictive thing for what the judge will do is the mugshot. Even this understates it because it seems like, oh, there's number 1, 2, 3, 4, 5. There isn't number 1, 2, 3, 5. There's number 1 and then a few other things. And if you formed a new predictor, deleting everything else and just focusing on the face, an algorithm that used just the mugshot and didn't know anything else captures about half of the predictable variation that there is in what the judge will do. In other words, 30 to 50% of what judges will do is determined just by the mugshot, which is not a thing I would have guessed. What's striking is what features in the mugshot appear to matter a lot. You might have think things like race, sex, gender, they all matter. They're not unimportant. But there are other features that are quite important that matter as much. For example, you can see in these two synthetic mugshots what the difference is. One feature is whether a person is well-groomed. Another feature that matters a lot that we discover from the algorithm is seen from these two photos, which is you might call fat-faced. Now, well-groomed, you're like, yeah, I guess it makes sense. Though I should tell you, the magnitudes didn't make sense to me. It's about half of the effect of having committed a violent crime or murder is just being well-groomed. But full-faced, fat-faced, if you ask people which direction does this go, are full-faced people more likely to be released or jailed? You get 50-50. It's not even clear there wouldn't be consensus on what direction it is. In fact, it turns out it's a very big effect, about the same size, as I said before. It's about half the effect of having committed a very serious crime, a violent crime, on release. And the direction is that people who have fuller faces are more likely to be released. So you can see that's another context, one where you might not have thought an algorithm could help us discover things. But not only do we discover better ways of identifying risk and releasing people who pose no risk that we somehow suddenly seem to think they do, but also better ways of understanding for judges to understand, wait, what drives my decision? I didn't realize that. And when we talk to judges, they're pretty surprised that these factors play a big role. And as you can see, it's very disconcerting, as you might imagine, and they would like to change it. The last example I'm going to do from the world of education, I'll do this a bit briefly. So in the world of education, there's a lot of AI that attempts to do the first path, which attempts to say, hey, what if we had an algorithm that can teach the way teachers do? You can go online to some of these online platforms and ask the question, and it'll give you an explanation, kind of like a good teacher. That's because it's trained on things teachers do, on explanations we have. But what if we were to train it on learning data? What would that even look like? Well, as a teacher, let me tell you what I think is the core problem for me, and I think for many teachers, the core problem of teaching, the core thing that I am ignorant about. I think it has to do with this maze on the left. I often feel like students, when they haven't fully understand, their confusion is a little bit like they're stuck in some maze. When I want to tell them, look, this is the right way to think about this. This is what it means to do blank. I'm telling them what the exit looks like. I'm saying, look for the red door. The red door is your exit from this maze of confusion. And they're saying to me, I don't see a red door. What should I do? I said, I don't know. Look for the red door. Because at some level, I can explain the right way of thinking about it. But I can't fully ever get, what are they exactly confused about? They themselves don't know quite how to say it because they don't know what the truth looks like. So being a student is very frustrating because you don't know what you don't know. And as a teacher, it's very hard to know what people don't know. So how would we build an algorithm? Imagine we want to build an algorithm that produced a map of this maze. What would that mean? That would be a cartography of confusion. It would be a map that said, here are all the ways in which students can be confused. If you knew that, then you would be able to easily probe and say, well, there are these 8 ways people, okay, let me just figure out which of them you are. Great, now that you're there, I know where you are in the maze, I know how to get you out. How would you do that? Well, you wouldn't train an algorithm on answers. You train an algorithm on the mistakes people make. And specifically, you'd say, let me get a bunch of data on people solving problems step by step, and let me understand what are the missteps, the errors they tend to make. If you've done all that, then you might be able to map the maze. Now we've started this process. And when we started this process, already some pretty striking things come out. I'll give you one example. In this data we have, we see that about less than 25% of students get the right answers. And these are hard questions. These are algebra questions. And these kids in 7th, 8th grade, they're kind of learning it. They're not getting it. But if you look at those same things, the ones where they got the answers wrong, more than 80% of the steps that they took were correct. Think of how confusing this must be. The student is not making a mistake. They're mainly getting it right. There's one part they're getting wrong, and then they're told, oh, your answer is wrong. You can do all the practice problems you want. How are you supposed to figure out which step it is that's broken? And what we think is, now that we're starting to be able to map the maze, we can identify which step is broken. And then we can focus practice problems, explanations. The teacher can be told, yeah, these are the kind of steps. The teacher can guide the people. And I think it's not unreasonable. We have a pretty audacious goal, which is I think we can cut learning time by a factor of 3, 4. Because most learning time is spent in the least productive activity of being confused, doing practice problems, not knowing what you got right, not knowing what you got wrong. We think we can get rid of that through something that has helped us discover something we didn't know. So let me conclude by just saying, in March of 1973, about a month before I was born, there was an article in Scientific American. This article has gone on to have like a little infographic that has become quite famous in computing. It involved animal locomotion. It said, how many kilocalories does it take for an animal to move a kilometer per kilogram of mass? And it's just plotted it. Here, I'll show you the plot. This is from the original Scientific American. Body weight on the left, the cost of locomotion on the right. There's a bunch of things. You'll notice some stuff. Mice, very inefficient, these little critters. Very caloric to move. People, somewhere in the middle, or as they were known back then, man, somewhere in the middle, somewhat efficient. Salmon is the most efficient animal here. And it's interesting to speculate why. It's like, oh, maybe it's because of the medium. Horses are also somewhat efficient. But the reason this figure has gone on to be so famous in the history of computing is for one data point on here. It's an interesting data point. It's an outlier. It's the most efficient data point on here. But it's not really an animal. It's this point down here. Man on a bicycle. And that's because a bicycle just makes people so much more efficient at getting around. It's more efficient now than any animal. What does this have to do with computing? What does this have to do with AI? Well, because a famous technologist looking at this said something very smart. He said, this is what computing should be, bicycles for the mind. Of course, this is not what computing looks like today, is it? It looks like a replacement for the mind. And I think this is the fork in the road. I think we have chosen the left path. I hope to have convinced you the right path is not just some imaginary thing. It is a very doable thing that we could be building algorithms. All the energy we could be putting on the left path, we could be putting on the right path. And were we to put it, it would be transformative for society. It would not just be a matter of, oh, some dollars, some jobs would be had. I think we could spur a new era of economic growth if we choose the path on the right. A couple of years ago, I was living in Chicago, and I like Chicago. It's a beautiful city. It's by the lake. And I made a very hard choice. The hard choice I made was to move to MIT. I loved MIT. I like being here, but my friends were in Chicago. And so what really moved me to come back? I think what moved me to come back is because I am sort of fundamentally committed to the idea of building these bicycles. So much so that now I'm starting a thing called the Bike Shop at MIT, whose sole goal is the building of these bicycles and to move the entire field to building these bicycles. And MIT is the perfect place to do it, hence my mid-cross country move. I think one reason to see why MIT is so great is that it's got a world-class computer science department, a world-class behavioral economics department. It's a perfect place to combine all these things you need to build those kind of computational artifacts that enhance human capacity. It's also the case that its mascot is a beaver. And what better place to go build stuff than a place that prides itself so much that it is dubbed the beaver its mascot. All right, thank you so much. I'm now delighted to welcome today's moderator to join me, Anne-Marie Michael from the Dean's Office.
Thank you so much, Sendhil. That was terrific. I have to say that as someone who's a long timer here at MIT, I was really thrilled to learn that you were coming back, and here you are. So it's really wonderful to have you here, and what a great talk. We have a lot of interesting questions from the folks who are online. So let me start. Well, let me just start. First of all, you just mentioned the bike shop, the idea of the man on bicycle and the efficiency of our minds on a bicycle. Can you tell us a little bit more about how you're shaping that here at MIT to start with?
Yeah, I'll just quickly say that, and then I'd love to get to questions. Yeah, I think the focus is on, I fundamentally believe the main thing we need to do is two things. One is the grad students and the undergrads here are just so amazing. I think they are the future, and I think getting them to throw their minds at this question of how do we build bicycles is kind of the fundamental goal of the bike shop. Because I think when these minds put their self to that question, I just think amazing things will happen. And the way we're doing that is that we are picking these sort of iconic hard problems. Like I gave you an example with education.
Right.
So I just loved how these students, when given a hard task, they just throw themselves at it. So I view the bike shop as curating these hard tasks and putting them in front of these students and saying, go.
That's great. I think that just talking about how you're working with students and your lab kind of falls into one of the first questions we got, which was how exactly is the AI solving problems that humans can't understand? Like if you could dig into that a little bit. And then, a follow-up question to that is how do we know its solutions are accurate? Like how do we know that those are good ones? So I don't, if you want to dig a little bit into that.
Yeah, this is a fantastic question. I think that it's related to, let me start with how, and then I'll point out a problem with the how that's actually a feature, not a bug. So the how this is solved goes back to the fundamentals of supervised learning. In the fundamentals of supervised learning, what we tend to do is we give it a data set where we say, like, here's this protein, here's how it folds. And then the algorithm continuously trains itself to do well at predicting the answer that we know to be the ground truth answer. The result is quite a complicated model. So for example, AlphaFold, how does it do it? Well, we know how we built it. What is it doing inside of this neural network? Well, we don't quite know. Now, is that a bug or a feature? I think it's a little bit of both. It's a bug because, boy, would we love to know. But it is a feature because we wanted to do something that we currently can't. It would be an additional hubris if we were to say we want to do something you can't, and we wanted to do it the way we already know how. It's like, well, then probably you're not going to make new discoveries. When you think of these algorithms as an interesting, different way of viewing things, then you come to accept the fact that they're a bit inscrutable to us is a good thing. And but then we really, for the second question, we must be confident they can do it. And the safeguards with protein folding, as with all these problems, is you have a data set that it's never seen of totally new instances. How can it show you it can predict proteins? Great, here are proteins you've never seen. Tell me what you say, and then we'll see how right you are. It's actually classic science. Classic science is theories make predictions on new things that they're right on. ML algorithms make predictions on new things that they're right on. That's how we test them. The key is the new thing, and to make sure that it's something it hasn't seen.
Thank you. That's great. Another one of the participants today said, thank you for explaining the difference between the approaches that are fundamentally different. And, should we be doing one versus the other or simply not, or what about simply doing both? And what's your idea of what's the complementary, are they complementary? Can they be, how do you see, what's your vision? You're going one path and there's another. How does it all work together?
Yeah. It's such a good question because it reveals a sort of a conceit I've taken, which is a rhetorical conceit. Like right now, trillions of dollars are going towards the automation path. And so as a result, I'm forced to say we should take this other path. And I think that the key point I'm trying to make is there's way too little money spent on discovery. Like it's tiny, it's not even 0.1%. And I think it's not because discovery is not lucrative. It's that somehow people have convinced themselves automation is even more lucrative. But it's not the biggest social gain. And there's plenty of profits in this direction. I think in an ideal world, we'd be doing both because there's some huge values in getting things that can automate a bunch of tasks that, that we don't want to be doing. That's great. That in an ideal world, there'd be a nice mix of the two. One would be helping take some tasks off of us. The other would actually be pushing the future forward. The reason I'm taking such a sharp claim that we're going on the wrong path is because a trillion to a billion or a trillion to like whatever it is, a million is not a pretty fair fight. And we're just underinvesting in one path. And so I think if I'm being honest, but I actually, Anne-Marie, if I'm being honest with myself, I'd say I'm glad people are doing the automation thing, but I want to learn new things. I'm excited about this path, just independent of everything I've just said. I love learning new things. And boy, I'd love an algorithm that kind of taught me something I didn't know. That's kind of cool. I think surely there's some conceit there. That's the curiosity of the human mind.
All right. Well, good, because I love this question. And so it's a good follow-up to what you just said, learning things we don't know. Someone said, could AI be used to decipher whale speech and other animal communication?
Absolutely. I think they're just
awesome.
Yeah, I think there's just one thing you need, like the power of these things. Like, let's do something we have lots of data on. Dogs. Suppose you want to understand whether your dog's barks contain more signal than you realize. The thing we need to train algorithms in this new way is it's always the same thing. We need some relation between the thing and the ground truth. Like we need to say, I don't know the relation between A and B. I'm ignorant, but I need to learn it. So with like, say we're building an algorithm to learn what dog barks mean. Obviously, I don't have a dog, so I'm using dog sounds. But anyway, what dog barks mean. You need to say, here's the bark and something about the ground truth. So there's actually a paper, I think it was in Science or Nature recently, that did this in a fantastic way, which is they got I think it was the sounds the elephants made, and they tagged which elephants were present when it made the sound. And they asked, are certain sounds associated with certain other? Is there a naming of elephant Bob? When Bob shows up, you're more likely to make the sound. And in fact, they saw it appears there are names, and these elephants' sounds are associated with these names. So if you start being creative in the collection of these data, I am sure we'll start to understand something as amazing as animal language. And so what a great question. Super interesting.
That's great. That's really fun to think about. Okay, now we're gonna so you put up a chart about GDP. So of course we're gonna have GDP questions too. This is an interesting one. Just asking, you said we grow our GDP when we innovate, right? But what about this is a large question, but maybe you want to think about, just say a few things about it. But how do we get global consensus on which AI to build versus, the financial goals that shareholders have? And like, that's a big economic question.
And I think it's worth talking about. I'll use this as a springboard to talk about something else that's important, and it's about how central places like MIT are, which is, I think the last 10 years, 5 years especially, have hidden how important universities are in the research and development pipeline. You even have people saying things like, oh, like LLMs were created by industry. LLMs were not created by industry. All of the core stuff came from research labs. But they were wonderfully scaled by these companies. That's not something any academic lab could do. We don't even know how to scale. This is not a thing that we're good at. Like academia is not good at that. So all the credit to these companies for the amazing work they've done scaling. But the seeds of invention have always come from academia because we just have the time and freedom to innovate. That's what we do. We try a lot of things. Most of them don't work, but some of them do. I'm saying this because while scaling and all of that can be kind of big dollars, big financial incentives push in this direction, you can shape the future by guiding the direction of the core R&D that's happening at universities. You really shape the future. When people in academia started saying, hey, we should be working on machine learning algorithms, then we started having breakthroughs. We started getting deep learning. That came from universities. Architectures that underlie the transformer came from universities. Even the transformer, people are like, that was a Google paper. Every single component of that transformer architecture was in a paper written by someone at a university. I'm saying this because while you can't shape the behemoth over here, we can influence what the top of the funnel, what the source of the stuff looks like. And I think what I found invigorating by being here at MIT is, like I said, that the students here are shaping the future. It may not be as transparent as when a big CEO at OpenAI or someone says something, but the students here are shaping the future by the choices they make. And I think if we can help them make better choices, we can shape the arc of this around the world.
Thank you. So that was a question about the GDP, and someone else asked, the GDP, chart is interesting, of course, but what about other indices out there that are connected to quality of life, like contentment, positive human connection, those kinds of things?
Yeah.
What could you say about, you talked about the two different types of AI.
Great.
Where, how's AI leading to better quality of life? If you could talk to the two models, or
yeah. Let me take a cheap answer to that, and then I'll take the more complicated answer.
Okay.
The cheap answer is there's actually pretty good data now that says as we get richer and richer, we do get more contented. We do get better food. But the truth is that's going to saturate. Like there's only so much good food and good vacations you can take. So as we get richer, there's a branch of work that says, actually, we're going to want to throw more and more money into the one thing that will dictate life, which is amount of life. And so I genuinely think medicine is a perfect instance of how these two are so different. Current path is like, let's save some dollars. It's like, okay, but you know what I don't want to save dollars on medicine. I want to spend more money on medicine that works, that helps me live a better life, higher quality life when I'm older. I'd happily pay more if you got me that. And so that distinction that you see between sort of quality and just cost savings is so clear in medicine. So that's a bit of a cheap answer, but now let me give the real answer. I think the real answer is deeply related to the question of what does it mean for a bicycle to enhance human capacity? I think once we think of these things as tools, we'll force ourselves to just take a step back. So even take a large language model that helps you edit a document. Once you think of it as it enhancing my capacity, you will say, oh, what would a good editing tool do that would make me a better writer? You would just build it differently. It wouldn't just say, oh yeah, I edited it to make it better. It would actually be pedagogical in nature. It would help me learn new words. It would help me improve my capacities. So I don't have an answer to this question, but I think it's the most important question is that once we take a design perspective to a bunch of these things, where the goal, like they said, isn't just GDP, but it's actually enhancing human capacity, contentment, all of these things. I actually think we'll just design these products quite differently, which is only half an answer, but I think it's the only answer that we can, which is we need to focus on those things.
Great. One question I had for you, and this is, I know a lot of our economists, you and others at MIT, are, really thinking about AI and labor and the future of labor. And, one part of it is what we know about AI, how we, different models of AI. Are they complementary? Are they substituting? But a huge part of this complex problem or challenge is policy.
Yeah.
I don't know if that was one of the first things I was thinking as you were talking. This sounds great to me. What are the policy challenges here? Like, where do you intersect with that or think about it in all the many things that you're trying to do?
Yeah, it's a great question. I think that one place where I think a lot about the policy levers is that I think if you look at the sort of the discussion on AI as a whole, whether it be on the left or the right, I think there's something very defeatist about that discussion on both sides. People act like it's a freight train. It's going to go in the direction it's going to go. And the only thing we can do if you're on the left is put safeguards on it, make sure, stop the train, or make sure it doesn't, hurt anyone on the way. Or if you're a believer in it, it's like, we just got to speed the train up. But the idea that there's a track, it's laid out, it's only going to go in one direction, is just so inhibiting. It's so defeatist. And so I think if the policy discussion could be enhanced to just get a sense that we're not just choosing how fast in guardrails, we're actually making this wide array of choices about what. I think it would feel very different. And I think a lot of the sort of lack of agency that people feel in the policy discussion, but in everyday life, it is because they have this feeling that this thing is just going and it's going to go in this direction no matter what I do. And I think that that is the most inhibiting thing. And I think I've often found in policy, people feel like you should give a policy suggestion. But I think more important than policy suggestions are frameworks or mental models. And I've often found if policymakers have the wrong mental model, it kind of just gets everything wrong. And I think here they have the wrong mental model. I think they're disputing how fast the train should go and what guardrails we have. They should be asking which direction do we want the train to go in?
Right. Thank you. So you gave a couple of examples within, education and, medicine and, sort of the criminal justice system. There was one question about from your research or, from others in the field, where, are there some other exciting real-time projects you could mention where really AI is helping people see problems in entirely new ways. Just a few other examples or areas where this is really exciting direction.
I'll give a few examples. I'll talk about some science examples. I have been working with some grad students and some faculty here at MIT, Connor Coley and Masha Connor, who are computational chemists. And chemistry is an amazing place, full of discoveries to be had. So some things I've learned from them, which I'm surprised at, but is amazing, is we have databases of 12 million chemical reactions, or 12 roughly, of these molecules become this thing. This is the yield. And you can build algorithms that do that very well. But when you take those same algorithms and try to get them to do work on a new reaction, they do much less well than a chemist. And it's amazing that even on such a structured problem as chemistry, humans seem to have a ton of insight that these algorithms are not able to discover. And what a fascinating place where we now are able to ask a question: how do you combine whatever tacit knowledge a human has with whatever explicit things the algorithm has found to be able to make breakthroughs in chemistry? I think the Chemistry Nobel Prize was awarded today, and 20% of those Nobel Prizes are given to just the task it's a hard task of finding reactions that synthesize stuff. And that's like the hardest problem. So I was surprised that chemistry is a perfect example of this. We tend to think of the hard sciences as, oh, there's a theory, no, actually, so there's quite a bit to be done. And I think in science as a whole, we're going to see an enormous flourishing. Let me give something from the very personal domain, the ultimately personal domain. Something that we could build in the next year that would be amazing for people, that would be transformative. I want to call it a mirror. So if you're a football player, like an NFL quarterback, after you play your game on Sunday, Monday or Tuesday, the coach sits with you and looks over the film and reviews every step you took, every misstep, every whatever. Wouldn't it be nice if we could have somebody who could look over all of the choices we've made and say, look, you tend to do this. I've noticed this. Is this what you want to be doing? Maybe even in just some controlled domain. Think of how many choices you make. Imagine you had your Alexa listening in on, hopefully not Alexa, but imagine you had a device listening in on all of your interactions with your kids. And then Monday evening, just like the quarterback, it could review the tape with you and say, hey, I noticed a pattern. You're always raising your voice more with this kid than this kid. Is that something you knew you did and intended to do?
Yeah.
I noticed this other pattern. Here are the times when you seem to get very angry. It has very little to do with what the kid did. Wouldn't it be nice if no one else ever knew, but an algorithm I could work with, just my algorithm, could go back to the tape, whether it's your job or your personal life, and could just help you see what are the decisions you make? How do you make them? Help you uncover things that you didn't realize you did, biases you might have, mistakes you're making. I think that would be utterly transformative. Like I was thinking, once I did that, maybe Zoom calls. All of us are on Zoom calls. What if something said, hey, I just want to point out, here's some stuff you do. Did you know you did this? You interrupt people a lot. You don't say much until the very end when the meeting's about that. Whatever you do, you may not know it. So anyway, the mirror, I think, would be an amazing thing to build. And again, not as a product that some company owns, but just something that you sit with and that you could understand. I would love that. And that's well within the realm of stuff we can build.
Wow. That's really interesting. I love it. Thank you for that. That's great. You should build it. I'll use it. I could use it. I'll be a test person for it. So one of the participants asked, well, what about, so you're working in the realm of AIs. So what about for those of us who don't work directly with AI? After hearing this talk and about these different paths for AI, what's a way we can think differently about the role AI plays in our lives right now? After hearing you, do these different definitions and tell us a little bit about the way AI could move forward.
Yeah, fantastic. Let me give some concrete things. So
Yeah.
most people in this call aren't going to be able to go out and build their own AlphaFold, but there are ways that you can do things you can do that are in the same spirit already with ChatGPT that are just typically, I think we default to using ChatGPT in this sort of automation mode, things that just save you time. But with just a tiny bit of help, you could default into I want to expand my own understanding mode. So here, I'll give you two prompts. Okay, this you can just type in. You can say, pick any one of the things I asked you to explain to me in the past. Create a small quiz on that to test whether I have understood and remembered it. And whenever I come back 1 out of 5 times, quiz me on one of these things. Now, that's just the simplest thing you do. Whatever you use ChatGPT now, something you learned in the past, you're now starting to not just like mindlessly have it go in one ear and the other ear. Here's another one. I've tried this one. This one works great. Teach me something that is easy to learn, but most people do not know.
Oh, I love it.
That one just taught me the difference between the word venomous and the word poisonous. Did you know the difference between those two words?
One has to be from a snake venom, and the other is any type of poison.
It's worth looking up. Yeah, I will. Let's leave it as a cliffhanger. People should look up. No, it is not snake versus non-snake.
Oh, okay. Right, of course. Other insects have venom. Oh, okay.
Interesting. Yeah. So, but and all I did was type, teach me something that's easy to learn. Most people don't know.
Oh, that's a great
So
one.
I think these two prompts, and you can come up with others. There's a creative world. Suddenly, it becomes less this mindless thing that's just kind of getting stuff done for you, and becomes this source of curiosity, this font of novelty. And I think that's something everybody can do and should do.
Yeah, it's great. It's working for you.
Yeah.
Yeah, that's great. So, someone wrote that you really challenge us to think beyond efficiency when it comes to AI. And, what would be a truly ambitious vision for AI in practice? I know you said that both things are going to be happening, but what would be an ambitious vision for the future of AI?
Yeah, that's great.
Great question.
Here's two ambitions, a human ambition and a science ambition. I think a human ambition would be one in which we have algorithms 25 years from now that let us, in a very seamless way, be much more reflective and thoughtful about how we behave and who we are, so that algorithms help us continuously grow as people. Because I think if I look back on my life, like most people's lives, I think most people feel this. They're like, oh, wow, in the last 40 years, I feel like I've learned so much. I really wish I could have figured this out much earlier. And some of it you can't figure out much earlier. You just have to live life. You just have to make the mistakes you make. But the truth is, I made a lot of mistakes before I learned. And if something could just help me grow as a human being, evolve faster as people, I think we all as a society would become far more enlightened. I think it would get us closer if all of us had, because it's hard to grow as a person. I think that would be the human goal I would have. I think the science goal I would have is that I think we could fundamentally reshape the very nature of how science is done. I think when you look back in the 15th century in Florence, when the scientific method really showed up, this is unbelievable flourishing. I think if we really apply algorithms in this way, I don't think we'll just have individual breakthroughs. I think it will change the nature of what science even is. And I think that will lead to the second scientific revolution that I think will be at least as big as the first one. So I think both of these goals are sort of personal and scientific. I actually think they're not just ambitious. I think they're very doable, and I think we should do them. So.
That's a pretty exciting place for us to end. This has been wonderful. We're at the end of our time. It really was thought-provoking, and we thank you so much. And we thank everyone who joined us today. Thanks from the Alumni Association and from MIT. And we look forward to seeing you again at one of these sessions. Thank you so much.